All right, this section, section 5, is huge, and that's why I'm chunking it into little pieces. So today is going to be section 5, part B, and we've done some work now with squares and square roots, and now I really want to get focused on classifying real numbers. So your learning target today, honestly, is going to look just like this, where we say, I can classify any real number. Any real number. Awesome. All right, well, now we have to talk about what on earth am I talking about? What does that mean to classify something? Well, we have kind of sets and subsets, and they fit into a category. That's really what classifying is, fitting it into a category. So we start with the most basic set of numbers, and these ones are called the natural numbers. Now you see this on your list, and frankly, sometimes this is called the counting numbers because these are the first ones you learn. When you're sitting on your high chair and you've got all the Cheerios laying there on your tray, that's what you first started, was counting. So frankly, just go ahead and start making this list. These are the natural numbers. It's natural to start counting 1, 2, 3, 4, and so on. This list goes on forever. It's infinite, so there's no way you can count them all, but those are the natural numbers, okay? Now, I've told you before, mathematicians get really efficient with their work, and so writing natural numbers gets to be a lot. So they've come up with kind of this super special alphabet all on their own, and an initial that actually stands for the natural numbers, and it's going to be a capital N, but it has a special way of writing the capital N, and they put like 2 lines in the slanted part of the capital N. I know it's kind of weird. Okay. Does it look like that, or does it look like this? Maybe it's 2 lines vertically like this. I'll put 2 lines everywhere. That's the capital N. That stands for the natural numbers. 1, 2, 3, 4. Okay. Next come the whole numbers. And the whole numbers are very similar to the naturals. In fact, it includes every single one of those natural numbers, and then it just has a little bit of an addition to it. So we have 1, 2, 3, 4, and so on, and we add 0 in there. See, it wouldn't make sense to use 0 when you're counting, so that's why we separate these two. These are the whole numbers, and the whole numbers have a special letter to represent them. Have you got a guess? Whole. Captain Obvious, it's a W, yes. So you make a capital W, but put 2 slashes in this downward stroke for the first part of the W. That's whole numbers, all right? Natural whole. Next come one of my favorites, and these are the integers. Okay, we've been working a lot with our computation skills with these guys, and the integers actually go in both directions. So I'm going to start in the middle with 0 and build my list in a positive direction, but then we have to do the same thing in the negative direction. And put your ellipsis dots there. It goes into negative land. So now, here we are. Okay? Alrighty. Those are the integers. Now, you'd think that the special capital letter that represents the integers is going to be an I, but you're wrong. Yep, knew it'd be too easy, don't you? The letter that represents the integers is actually a capital Z, and we put like 2 slashy lines on the slanty downstroke of the Z. Those represent the integers. Why? Why does Z represent the integers? It comes from German, I think, the word for numbers. Something like Zahlen, I think is how you say it. Okay. Don't ask me. I didn't make the rules. This is the way it is. Okay. So natural numbers, N. whole numbers W, integers Z, and they all have that extra line in that downstroke, okay? Cool. All right, next, now we're going to get really, really broad because rational numbers become so many, there's no way we could list them all. There's tons of them. Basically, this is any number that can be written as a fraction, okay? And the key here is that the fraction itself, when we make the fraction, and I'm going to put just like variables A and B on there. So as long as you can write it this way, with some number over another number, where these two guys are integers. So you wouldn't put like a decimal number in the top of your fraction. We're not talking about putting fractions in fractions. I just want a simple fraction. These two guys are integers. Oh, I can't even spell. G-E-R-S, integers. Yep. And there's one kicker because there's an old rule here that you cannot divide by 0. So B, no way, no how, can equal 0. All right? But basically, every single stinking fraction is a rational number. So that means 1/2 or 7/10 or 48/5. Yes, even improper ones. Absolutely. All of these work. Psst, do you know what else works? -1/2 or -3/4, and so on and so on and so on. Aha! I could have -83/2. That works. See? The negative, they're integers too. So all of these things are rational, and gets better. A number like this, I can write 3 as a fraction. Just go 3/1. I can put 0/1. I can say -8/1. So rational numbers are huge. There are several of them. Not several. That's ridiculous. There's an infinite number of them. Can never count them all. And every single natural number, whole number, integer is also rational. So they kind of fit inside this big, huge box called the rational numbers. All right. Really, this incorporates almost every number you can think of because almost every number can be written as a fraction. Okay. Now, when we think about that, numbers like 1/2 and 7/10 and -3/4, those are really easy to also write as a decimal. And in fact, you'll notice in your notes right here that included in the rational number part, I've kind of broken it into 2 categories, terminating decimals and repeating decimals. So let's talk about that because decimals kind of fit in right into this category. A terminating decimal, terminating means that it stops, it ends. Okay, at some point it just, now it might stop right away, like 5/10. It might go a little ways, like 0.75. Okay, but eventually it just stops. Boom, all done. These are terminating ones. Notice that 1/2 is the same as 0.5 or 5/10. So see, my fractions fall into really either one of these 2 categories. Either I have a fraction that terminates, like these nice ones here, or it's a repeating decimal, like, let's try 1/3. Do you remember what 1/3 looks like as a decimal? 0.33333. It never stops, never ends. There you go. Go figure. Something like 5/6. 5/6 looks like this, 0.0 or 0.83, and the 3's repeat. Okay. Eventually you get to that point and something repeats. All of these repeating decimals come from a fraction. All terminating decimals come from a fraction. So these two guys are rational. Okay? It's just another way to write a rational number. So when I look at my big pile of rationals, really everything in there also is either repeating or terminating. Okay? Now, let's hop back here for a second because I didn't give you a letter to stand for rational. There is one. Okay? And I know you're going to think it's R and it's not. Here's what we use. Q. And so what I do is I kind of put this extra little line inside the circle of the Q. Q. Okay? Aha! So, I wonder what Q is from. I'm not certain. I think it might be quotient. You could look that up if you wanted. Okay. Now, we don't really have a code for when we write terminating or repeating. So here's what I want you to write when you classify it, just so that we don't have to write terminating decimal, repeating decimal. Gets kind of long. So how about for terminating, we put a capital T little m. Terminating. For repeating, put a big R little p. Don't put any extra lines in there or anything. Okay. This is just the way we're going to get real specific when we have a rational number. I want you to say, oh, yep, this is rational, and it's either a terminating decimal or a repeating decimal. Now, you'll notice, though, that decimals really come in three types. Yes, terminating ones. Yes, repeating ones. And what's the third one? The third one is the strange one. The third one is the one that doesn't behave well, meaning it's unpredictable, it's bizarre, it doesn't make sense, I don't see a pattern. What is going on? That's what we call the irrational numbers. When you try to write them as a decimal, so I'll say as a decimal, they never repeat and they never terminate. Never repeat, never terminate. In other words, they never stop. I bet you can think of the most world famous, fabulous, irrational number. Pi. But pi is not the only one, because pi starts at 3.1415926 maybe, and then it keeps going. There are an infinite number of irrational numbers. Not just pi. There's more. As you get higher up in math, you'll see some more, like e, phi, okay? But there's a whole bunch of ones that you've already seen. Not kidding. The square root of 2. Yes, the square root of 2. 2 isn't a perfect square. So when you plug this in on a calculator, you get something like 1.414, and it keeps going, and it fills up the screen. And if we had some magical calculator that would go on forever and show you that display, never repeats, never terminates. What? Square root of 2 is irrational. It never stops. The square root of 3 is irrational. It's a freaky, weird decimal. It's around 1.6, I think, or 1.57, something like that. Never repeats, never ends. Weirdo. The square root of, I can't say 4, because remember what the square root of 4 is? That's exactly 2, which makes it a beautiful natural number. So I can't say square root of 4, but I can say square root of 5. Yep. Square root of 6. Yep. Square root of 7. Yep. Square root of 8. Yep. Square root of, not 9. Square root of 9 is 3. 10, 11, 12, 13, 14, 15, not 16. 16 is a perfect square. Square root of 16 is 4. And so on. Do you see what's happening? Got it. Okay, so anything with a weird radical sign that's not a perfect square, going to end up being irrational. Isn't that amazing? That's amazing. Do we have an abbreviation for this one? No, we don't. So what I do is I cheat, and I just want you to write capital I like that. That's not like something you'll see in any other textbook. That's just yours and my little abbreviation, okay? All right, all of this together give you the real numbers. So for the reals, say all rationals numbers. If I use the hashtag symbol, I mean numbers, okay? It's also all of the irrational numbers. And when we put all of those two together, that makes this one giant set called the real numbers. The real numbers get the big old capital R with two little slashes or two lines coming down for that one, okay? Cool. So this is how you're going to classify numbers. So let's take a look now. If you turn on to the back of your notes, you'll see that I've got a whole bunch of examples here. Okay, and I want you to write down all of the classifications for it. Okay, so the first one I think I give you is -32. Okay, now if you're going through the whole list, and you can kind of flip back there, is this a natural number? No. Is it a whole number? No. The first category it falls into is an integer. Okay, now you can write the words if you prefer. I'll put the symbol and the words so you can see. Now, if you're an integer, you are automatically included in the rational club. You're automatically rational. Okay, if you're rational, you can tell me something about when it's written as a decimal. Is this rational number a terminating decimal or a repeating one? This one's terminating, okay? Actually, it doesn't even go past the ones place, so it's terminating. Now, irrational? No. Either you're rational or you're irrational. You can't be both at the same time. This definitely, most definitely is real. In fact, almost absolutely everything's going to end up being real, okay? All right, let's look at the next example. 5, +5. Holy Hannah, you're sitting back in your high chair counting Cheerios. Those are the counting numbers. So this guy, I guess the two lines go on the downstroke of the end like this. This is natural. If you are natural, you are automatically a whole number. When you're a whole number, you are automatically an integer. And when you're an integer, you are automatically rational. What kind of rational is this as a decimal? It's a terminating one. There's not even anything past the decimal point, so it's definitely terminating, and therefore it's real. That pretty much gets as many names as possible because it can't be irrational. How about 7 4/9? That's your next example. Okay, 7 4/9. It is not natural. It's not a counting number because it has the fraction, which means it's not whole, not an integer. Integers have to have whole part or no fractional parts. So the very first name we can give this guy is a rational number. Okay. What kind of decimal would this be? Is 4/9 a terminating decimal or a repeating decimal? Do you know? 4 divided by 9. Watch what happens. This goes in here 4 times. 36. Subtract 4, add a 0, bring it on down. That's 4. 36. What's happening? What's happening? This thing is never going to stop. It's a repeater. So put a capital R little p to stand for repeat. If I say it's rational, can't be irrational at the same time. It's one or the other. So this guy's rational, which means the only thing left to classify it as is a real number. I guess I incorporated all that into one, didn't I? There you go. So that's 7 4/9. All right, let's see. Next, you have negative 12. Negative 12. Not a natural number. Nope. Not a whole number. But it is an integer. Okay, that's an integer. If you're an integer, you're automatically rational. What kind of decimal is that? That's a terminating decimal, and it's real. So that guy gets 4 names. Last one, square root of 10. The square root of 10, the square root of 9 is exactly 3. So this is going to end up being some weird decimal that's probably like 3.1, blah, 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 blah. Goes on forever. So natural, no. Whole, no. Integer, no. Rational, can you write this as a fraction that would stop as a decimal or repeat as decimal? No. This is the weird one. We call it irrational. In addition to that, being irrational though, it still is real. Real pretty much includes almost everything. Okay? All right, that's a lot to absorb. I need you to get used to these abbreviations so that you can classify any number into all of its classifications, all of its categories. Okay? Once you get familiar with how these look, it'll become more and more automatic. So, what I've got for you is a worksheet today. Okay? Go ahead. And if you can't find the worksheet, go on to Schoology and check there. Okay? Classifying numbers. You might want to write all of those classifications from your notes at the top of the worksheet. And as always, good luck and may the force be with you.